going to talk about automated shades and how they try to participate in the performance and the goals of the New York Times building. And to do that, I'm going to borrow an excerpt from the performance specification that we bid on. And in this section, it lists 6 major goals for the automated shades. We'll have time to illustrate 4 of them tonight. Maybe have a chance to talk about the others later during the discussion. The first 3 goals are to maximize natural light that comes into the space, to maximize the occupant views to the outside, and yet at the same time to prevent the direct rays of the sun from hitting people and making them hot and uncomfortable while they work near the window wall. These are seemingly contradictory requirements, and that means we're going to have to optimize the performance of the shades and pick the optimal position of the shades in the building. In order to do that, we need to have some understanding of how the sun moves around the building. And what we have on the left is a little hard to see. There's a footprint of the New York Times building. There's due north, and the building is rotated roughly 28 degrees, as is the typical New York City grid. So north is not north as far as the building is concerned. And we can see the winter path in plan here. Rises in the southeast and sets in the southwest. The summer, June 21st, is a much broader path, and then the spring and fall fall in between. In section, looking at the southeast elevation at noon, the sun is as high as 72, 73 degrees, but in the winter, January and December, it's fairly low at 24 degrees or so. So the sun is very dynamic. Every day it's slightly different than the previous day, but it is a predictable path. And so we use a central control system, our AAC solar trap, that we can program with the profile of the orientation of each elevation of the building, some aspects of the architecture, the latitude, and with that software we can project when a ray of sunshine will fall into the space of the building and help us determine where to put that shade on a given side at a given time of day, any day of the year. The system will also receive input from sensors on the building. There will be 3 radiometers mounted to the mast of the building that will measure the amount of solar radiation and compare it to an ASHRAE clear sky value for that time of day for this location. So in this illustration, we have a partly cloudy day around noon, and then the yellow line matches up with the theoretical clear sky, so the afternoon shows it was a sunny day. Now, if it's cloudy out, the shades will stay up, all other things being equal. There are many other things to consider. And on a sunny day, the shades will move according to the angle of the sun. So if we take the clouds away, the radiometer on the roof will determine that it's sunny out, and the computer will calculate where the shade has to go in order to keep the person near the window wall in shadow. 90% of the project is open plan, and in the typical open plan area, it was determined to allow the sun to come in about 3 feet from the window wall. So the shade in this illustration, facing south on December 21st with the low winter sun, the shade has to go pretty far down the window. If we take the same condition in the summer, same orientation, June 21st, the computer will determine that the shade only has to go roughly 1/4 of the way down in order to provide the same allowable 3-foot penetration, which gives us the irony that we need the shades more in the winter than we do in the summer, typically. One of the aspects of maintaining views to the outside and maximizing the amount of natural light that can come into the space is to recognize that the building is in the urban environment, that there are shadows that will be cast on this building by other buildings, and the specification requires that we detect or determine this shadow condition for what is known as a shade control zone. And when a shade control zone is in shadow for, let's say, 30 minutes or longer, we need to be able to raise the shades. In order to do that, with the assistance of the New York Times, we secured a 3-dimensional map of a 6-block radius surrounding the building. And with the help of an outside consultant who was able to plot the movement of the sun and project the shadows on the building, we were able to create a database where every individual window in the building can be plotted for 365 days of the year. And with this database, we can now string together a group of windows into a zone. And when a zone will be in shadow for 30 minutes or longer from this database, we will be able to raise the shades and again let the natural light into the space and give the occupants the view to the outside. This is a movie created. Oops, hold on. We'd really like to see this movie. Right. Oh well. It was a cool movie. You have to take my word for it. That was going to show the shadows moving across the. I'm going to just try one thing. There we go. All right, and so you'll see this is the east elevation of the building in the morning on June 21st, and you can see the shadows from the surrounding buildings as they move across the facade. And because the New York Times is taking the lower half of the building, there are many opportunities to raise the shades because of the shadow condition that is created. The fourth and final criteria that I'm going to illustrate today is the fact that we have to maintain a glare-free environment. The assumption is that, or what we learned in the mock-up is that the vision glass, sometimes there will be a condition where the shade may only be partway down based on the solar tracking or the cutoff of the sun and the allowable solar penetration. But below it, there might be a glare condition created that would require the shade to come down, let's say, in an override mode. An example would be a bright, overcast day. Remember, we have a glass that lets in 73 or 74% of the visible light. And so it's quite possible on a bright, overcast day that the brightness in the window wall might be greater than what might be considered comfortable for the worker. So the specification that we are performing to says that when we determine that the average luminance in the unshaded portion of the vision glass exceeds 2,000 candelas per square meter, which is that we need to bring the shade down to a predetermined point to put the worker or occupant in comfort and protect them from visual discomfort. To do that, we put in light sensors, typically on a column, for example, that looks out at the window and measures that brightness and sends that information back to the central control system, which would then bring the shade down to a lower position, if necessary, to provide that comfort from glare. So there are two other criteria that we don't have time to illustrate. One is a manual override system, and the second is the ability to line up the shades and make them look nice and neat